So I do two of you. Wait for 2 3 more minutes. Let your friends join. Still only two of you. Can you text your friends, please? Ask them to join soon.
Yes, sir.
Srivatsan and one more guy is there. Srivatsan and Siddharth. Yeah. Four of them. So we'll wait for 1 more minute. Okay, fine. We'll start. Let them join if they're joining. Okay, so people, so we have been seeing, we just started with, I think, resonance, right? So we saw how to draw the resonance structures of benzene, like if I have any other groups present, electron donating and electron withdrawing groups, how do you write the resonance structures? And with that, I told you, I know that benzene and its derivatives undergoes electrophilic substitution, right? I know what is electrophilic substitution, right? So a positive charge getting replaced by another positive charge, right? So from the resonance structures, right? If you have an electron donating group like say phenol or NH2, something like that, right? So you saw that with the resonance structures, with the negative charges are getting formed at ortho and para positions, right? So that is why electron donating groups are going to be ortho para directing, right? But say when I had NO2, right? So you saw negative charges are getting formed only at meta positions, right? So obviously, electron withdrawing groups are going to be meta-directed, right? It's all about wherever the negative charge is there, the positive charge will come and attack there only, isn't it? Right? So that is where we stopped last class, right? So we'll continue with resonance, right? Fine. So that is one of the application of resonance, right? To determine whether the particular group is going to be ortho para directing. There are so many applications, I would say, right? So we'll go on, right? So with the help of resonance, sometimes I'll be able to determine the stabilities of carbocations, carbanions, and all these things are possible, right? So we'll take some examples, right? Say I take this example, a simple example. Say I have CH2 double bond CH CH2 plus. Okay. Now this is what these kind of carbocations are what are called as allyl carbocations. You know, hopefully you know what is an allyl group, right? So you must have studied allyl halides, allyl alcohols, isn't it? So there are two things, right? So I have something called as allyl and I have something called as vinyl, right? So can someone tell me what is the difference between these two, allyl and vinyl?
Sir, vinyl is CH2 double bond CH.
Okay.
And allyl is that CH2 double bond CH single bond CH2.
Okay, fine. Partially correct. So the thing is, we are going to talk about the functional group, or say in this case, it is going to be a carbocation, right? So where the positive charge is present, or say where the functional group is present, right? So depending on that, I'll be able to differentiate between your allyl and vinyl, right? So in case of allyl, right? So you have an sp2 hybridized carbon, obviously because you have a double bond, right? So you have an sp2 hybridized carbon, but the functional group or say the positive charge is not going to be on the sp2 hybridized carbon. It is going to be at the next carbon, which is going to be sp3 hybridized. You can see that here, right? This is sp3 hybridized, this is sp2 hybridized, correct? So the next carbon atom after the sp2 will be sp3, and there if you have any functional group or a charge, that kind of groups are what are called as allyl groups, right? Now if it is going to be vinyl, I can give you the example like this. Say CH2 double bond CHCl, or say I can even put a positive charge, right? Now what do you see here? The positive charge or the functional group is directly with the sp2 hybridized carbon. Okay, right? That is the basic difference. Allyl, it is attached to sp3 hybridized carbon, even though I have an sp2. In vinyl, it is directly attached to the sp2 hybridized carbon. Okay, anyways, so we are talking about this. We'll talk about that. Fine. So I'm telling that this carbocation is highly stable, right? Now, how will I prove it? The only way to prove it is the help of resonance, right? So what can happen now? You can see that there's a double bond and this carbonate, oh, this is not sp3 hybridized, this is sp2 hybridized only because it's a carbocation, I'm sorry. Because if it was a functional group attached, say if it was something like this, then it would have been sp3 hybridized. Okay, so there a mistake. So this is a positive charge. Okay, so this is my allyl carbocation. So I'm telling you that this is going to be stable, and I'm going to prove it that this is going to be stable with the help of resonance, right? So now how will I prove it? Say now this bond which I have here can directly now see. I can make two steps and make you understand, or I can directly put it in one step. It's going to be a little easy also. So anyways, for the first time being, we'll do 2 steps. Okay. So the pi bond which I have here, right, is going to undergo heterolytic cleavage. Okay, right. So now you can ask me, sir, heterolytic cleavage, I understand, right? So that means if this undergoes heterolytic cleavage, either this can get the electrons or this can get the electrons, obviously, right? But obviously, here I have a positive charge, right? So definitely it is better to put the negative charge here to this carbon atom, right? To this carbon atom, right? It is better to put the negative charge than to this carbon atom because positive negative will have attraction. It is easier, right? So please understand one more thing, right? So whenever you go for charge separation, that means say this particular bond is neutral now. I'm talking about these two carbon atoms, first two carbon atoms, right? So these two carbon atoms are neutral, right? So whenever you go for this charge separation, in the sense the bond breaking happens, the charges are formed, that actually requires some energy. Okay. So again, not only in this, in any chemical reaction for that matter, right? It will undergo a pathway, right? That chemical reaction will undergo a mechanism or a pathway, right? There, the energy expenditure is minimum. Wherever I have minimum energy spent, right? That path only the chemical reaction will take, right? And obviously here, in this case, if you put a negative charge here, I'm going to spend a lot of energy, right? But if I put the negative charge here, since I have a positive charge here, I'm going to have attraction, so the energy spent is little less. Okay, so now I'll put the heterolytic cleavage like this. Okay, so now what will happen? I will have CH2 plus. Now this has lost electron, and I have CH minus and CH2 plus. Done. Now what will be the next step? I have 2 electrons here, right? Now this will come here, make a bond, and the negative charge is gone. Positive charge is also gone. So you will end up with this, isn't it? Right? So obviously now what is happening? Because of resonance, the positive charge is getting stabilized, right? So again, I would say that this carbocation is little stable, right? Okay. Now this is an example for primary allyl, right? This particular carbocation, what I have here is called a primary allyl carbocation. Okay, I can have even secondary and tertiary allyls also. Say, how will I put it? It's like this: CH2 double bond CH. Say CH double bond CH2. I have a CH here. I can have a positive charge. Now, what do you see? I have one allyl group, second allyl group. So this is going to be called as secondary allyl carbocation. How will be tertiary? Tertiary will be looking like this. CH, again one more allyl group, here one more allyl group, again a positive charge on this carbon. Right? Now this is my tertiary allyl carbocation. Right? Now tell me, primary, secondary and tertiary allyl carbocation, which do you think is more stable? I mean, can you arrange them in the order of stability? Hope you understood my question. I have primary, secondary, tertiary allyl carbocations, right? I'm asking you, arrange them in the order of stability. What will be your answer? If you don't know, you can guess.
So
That's
primary
obviously
will be
there.
more stable.
Sorry?
Primary will be more stable.
Primary will be more stable. Okay, someone said secondary, primary, and tertiary. Okay, any other answers? Or any reasons, Kana, why primary is more stable? Why did you think that? Or someone said it is secondary is more stable. Why do you think secondary is more stable?
More resonating structure. So
Okay, correct. That's the way to approach it. So if I talk about more resonating structures, more resonance happening, right? According to that, then which should be more stable?
tertiary, sir.
Good. Obviously, right? So that's the way to approach. More and more is the number of resonating structures. More and more is the resonance. More and more is the extent of resonance. More and more is the stability. right? So here you have only two resonating structures. I would say this you can consider or you cannot consider. I would say okay, three resonating structures, right? Here you will have so many like this. Here you have again, I would say one more time that, right? So definitely tertiary allyl group has more resonating structures. The bond can come here to here, or it can come here, or it can come here, right? So there are three sides. From three sides, resonance is happening, right? So definitely tertiary allyl. This is okay. I can write tertiary allyl, secondary allyl, and the least stable in this case would be primary allyl. Okay, everybody got it? What about the steric hindrance in tertiary? Okay, fine. Fine. Harish, so the thing is, we talk about steric hindrance. Okay, first of all, I don't know how many of you know what is steric hindrance. Steric hindrance is the crowding, right? The bulky groups present. Like obviously, you know that here it is going to be, what to say? Here it is highly crowded because I have three allyl groups present, right? We talk about steric hindrance only when I go for chemical reactions. Say, for example, right, I have a nucleophile coming, right? Say I have a nucleophile, say Cl minus is going to attack all of these carbocations. Okay, so at that time, definitely what you say is going to come into the picture, right? So obviously this is more crowded, so the Cl minus will find it difficult to attack this carbocation, and it will find it very easy to attack this carbocation, right? But stability, if I speak, it is not with respect to any chemical reaction, right? It is just that this is there, whether it's stable or not. Obviously, and okay, even if you put it that way, right? So if I talk about, say, this is more stable, this is the most stable one, right? And obviously, when I compare, when I connect stability with reactivity, okay, so obviously, highly stable species will not react much, right? But a very less stable species will be highly reactive, right? So either way, the answer which I gave you for this Cl minus will find it difficult. That will be slower reaction here because it's highly stable, as well as I have very high steric hindrance, right? But here it is least stable and it has least steric hindrance. So the reactivity of this will be the highest. That makes sense. Okay, oh, hope I
Thank you, sir.
answered your question, Harish.
Yeah, sir. Yes, sir.
Okay, cool. Yeah. So what I was telling, yes, so this is the order of stability for allyl carbocations. Okay, now I can go for even, okay, fine. Next, if I go for I had a new duster. Oh, 1 second. Yeah. So now let me take this one, right? Right. I have, this is my phenyl carbocation, right? So I have phenyl carbocation. Is it not? See, there's a difference between phenyl and benzyl. This is also called as benzyl phenyl or benzyl carbocation. Okay, cool. So now again, this is going to be stable, right? Okay, so how? Well, okay, fine. Now tell me, where will you start the resonance structure? Where will you start the resonance from? Okay, so let me mark the carbon atoms. 1, 2, 3. Where will I start the resonance from?
3, sir.
Yes, right? So we'll start the resonance structure from 3. So because there is no lone pair, there is nothing which can come back, right? So only way I can start the resonance structure is by breaking this pi bond. Okay, so obviously again heterolytic cleavage will happen, and then or I can directly put, say, this bond goes here, make a bond. So now next structure would be a double bond CH2 would have been formed. Now the third carbon atom, which is marked 3, right, which is going to lose electrons. So I'm going to get a positive charge here, a bond, a bond. So again, what will be the next structure? Next structure would be this will come here. So I can write double bond CH2. Now the positive charge is gone. Now the positive will be got by this carbon atom, and there is a bond here. Again, this will come here. Say now the positive charge is gone, a bond here, a double bond CH2, and now the carbocation is formed here. Where is the bond? Here is the bond. Again, this will go, everything again will happen, right? So you see, again, because of resonance, right, the positive charge is getting stabilized. Okay, so again, this is an example for primary phenyl carbocation, right? I can even have again secondary and tertiary phenyl carbocations, right? So how will it look, right? Okay, secondary will look like this, CH plus PH, PH. Okay, the PH represents the phenyl group, like this one, C6H5 group, PH, PH, CH plus. This is my secondary. Tertiary will look like this, PH, C plus PH, and one more PH. That is phenyl, right? So yeah, this is primary, secondary, and tertiary phenyl groups. I mean, phenyl carbocations, right? So again, how do you think is the stability order of this? Yeah,
Tertiary, secondary.
correct.
primary.
Yeah, correct. So obviously, again, more and more is the resonance, more and more will be the stability. So obviously, tertiary has three phenyl groups. So the resonance process can happen from three directions, right? Here I have only two, here I have only one. So again, the order of stability will be tertiary phenyl, secondary phenyl, and primary phenyl. You can write it. Okay. Primary phenyl. Okay. So these are all the different carbocations I can have, right? Okay, now we have studied primary, secondary, tertiary, primary allyl, secondary allyl, tertiary allyl, and I have, what is this? Tertiary phenyl, secondary phenyl, primary phenyl. Now I'm going to put all of them together and I'm going to give you the stability order. Okay, so many of them are there. We are going to start, like obviously, okay, we'll see the order now. Comparing to I'm going to put everything in one picture. I'm going to give you the order. Okay, hope everyone has taken it down. It's easy resonance structures. Okay, fine. So the most stable of them all, right, among all carbocations, the most stable of them all would be tertiary phenyl. Okay, right. So tertiary phenyl is the most stable one. Okay, next I have obviously coming secondary phenyl. Okay, then I have okay, secondary phenyl with tertiary. Okay, fine. So the thing is going to look like this. Secondary phenyl has almost same stability with tertiary allyl. Okay, and after that, I'll write it here. After that, I have secondary phenyl. Oh, secondary phenyl is over. Okay, so primary phenyl will have almost same stability with secondary allyl, and then comes your tertiary, normal tertiary, and then comes your primary allyl. Okay, then obviously the last two ones, primary and your CH. So this is the order of stability. Okay, so you have tertiary phenyl maximum stability, secondary phenyl and tertiary allyl will have same stability, and primary phenyl and secondary allyl will have same stability. After that, normal tertiary carbocation, then your primary allyl, then secondary, primary, normal carbocations, and last would be CH. Okay, so it's better to remember this order. Okay, it's easy only to remember because you know obviously the logic behind this, right? So this is the overall stability order of all the carbocations possible. Is that okay? Right? Fine. So now same thing can happen with your carb anions also, right? Say I can even have again primary allyl carb anions, all those stuff. Say I can do it like this. Say I have CH2, CH, CH2 minus, right? Now tell me, where should I start the resonance structures from? Say if I mark it as 1, 2, and 3. where should I start the resonance structures from? Three. Good. Yes. So because I now see, you cannot put the bond here. See, if I put the bond here, this absolutely makes no sense. Why it doesn't make any sense? Can someone tell me why I should not put it like this? I mean, I'm putting the bond directly here to this bond. Why I should not put it like this?
Because the
Electron.
carbon next to the double bond will already be negatively charged.
Okay, fine. I can accept it, but not a perfect answer. For resonance to happen, one thing is that I should have 5 electrons, obviously. What is the second condition? See guys, the thing is, okay, I have 5 electrons both sides, right? But I should have some space available inside the atom for the electrons to be occupied. Is it not? So that indirectly I'm telling that I should have an empty p orbital for this electron to go here. This carbon atom should have an empty p orbital, and do I have that there? Do I have it here? Empty p orbital?
No, sir.
Why?
Because there's a charge present.
There is a charge present. That's not the way you answer, Kana. Okay, there is no empty p orbital. Why there is no empty p orbital? I'll give you 30 seconds. Please think. Why is there no empty p orbital, or how will you prove it? If I tell you the answer, then you'll say, yeah, sir, correct.
Sir, carbanions do not have empty p orbital.
Exactly. That's what I'm asking. Why? Okay, 30 seconds got over. The answer is because it is sp3 hybridized. Is it not? All three p orbitals are occupied. How will I have an empty p orbital? But here these two are sp2 hybridized. In case of carbocation, at that time it was sp2 hybridized. Again, I had one empty p orbital. Hope you understand what I'm telling, right? So this cannot happen because this doesn't have an empty p orbital because it is sp3 hybridized. Okay, so anyways, so again, I think you're kicking yourself. Please kick yourself, right? If you're not kicking yourself, right? Okay, so if I write the resonance structures, so I have a carbanion. So now I obviously, as you said, the resonance structure has to start from this carbon atom. So this will come here, this will break. So you will have, yeah, these two are the possible resonance structures, right? So again, I can have primary allyl carbanion, secondary allyl, tertiary allyl. All these are possible. Same with benzyl, CH2 minus, if I have, okay, I write the minus properly. Okay, minus, right? So again, I have to start it from here. Now 2 electrons, this will come here, this will break. CH2, a negative charge, and this, then what will be the next step? This will come here, this will break, right? So again, all these will continue, CH2, right? So again, because of resonance, even carbanions are getting stabilized, right? So again, I can give you an overall order for carbanions. right? Okay, so I hope you have taken this down. It's very simple. So this is for carbocations. Now we'll look the order for carbanions. Okay, so again it will be tertiary phenyl, again because of more resonance, then secondary phenyl of all approximately equal to tertiary allyl, then comes your primary phenyl, again almost equal stability with secondary allyl. Now there'll be some differences, right? Then it will be directly primary allyl, then it will be primary secondary tertiary. Yeah. So hope you understand why this is happening. We already looked at this. This is because of inductive effect. Right? In primary, I have only one electron donating group. Secondary, I have two electron donating groups, and in tertiary, I have three electron donating groups, increasing the negative charge. More and more charge, less than the stability. Right? So this will be the order for carbanions. But most of mostly you will not be using carbanions. 90% of times the questions will come only from carbocations. Very rarely you will see questions coming from carbanions. Is that okay? Right? Fine. So that is about your carbocations and carbanion stability with respect to resonance. Again, this is the overall order comprising of everything: inductive effect, hyperconjugation, as well as resonance. So obviously primary, secondary, and tertiary. In carbocations, we can use either inductive effect or hyperconjugation. But if I go for allyl and phenyl groups, there I have to go for resonance. And here again, primary, secondary, tertiary here will be inductive effect, and all the other things will be resonance. Obviously, hyperconjugation is not possible for carbanions. We already know why. Again, the same reason that they don't have an NTP orbital, all are sp3 hyperconjugation. Is that okay? Right. Cool. So that is about carbocations and carbanions. So next thing what we do is, with the help of resonance, right, we will try to determine the acidic and basic strengths. Okay, right? So we did those things only with respect to inductive effect. Is it not? Now we'll try to include resonance into this. Okay, and we'll see how are we going to determine the acidic and basic strengths, right? Okay. Start. Any questions till now, people? Any doubts?
No, sir.
Okay. Right. So let me start with that. Okay. You want to start with acidic strength? Okay, we'll start with basic strengths. It's a little easier, right? So basic strength, right? So if you can remember, right, we already decided the basic strength with respect to inductive effect, and I'm talking about the gaseous phase. Obviously, if I go for aqueous phase, it will be different, right? So if I talk about gaseous phase, I said that tertiary amines. Okay, we're talking about amines, right? So tertiary amines are more basic than secondary amines, and secondary amines are more basic than primary amines. And then comes your ammonia, and the least of them all would have been aniline. Is it not? Right? So again, this is what we are going to concentrate on. Okay, this we already did, this part. Right? Now we'll concentrate on the other parts. Basically, not only aniline, anything which has resonance. Any amine which will have resonance, obviously I'm going to have a problem. The basic strength would have been highly decreased. Okay, so aniline we know how, right? So it's all about, okay, if we talk about basic strength, what is the criteria? The criteria is going to be the availability of lone pair. More and more is the availability of lone pair, more and more will be the basic strength. Right? Again, we used inductive effect. We said that in tertiary, I'm going to have 3 electron donating group, increasing the availability of lone pair on nitrogen, and that's why it's more basic. And here we said aniline is going to be the least basic. Sorry.
Yes, sir.
Okay, because I got a call. That's why. So what I was telling is, yeah. So I have aniline, right? So here the lone pair is not even available on nitrogen because it is going to involve in resonance. Is it not? This will come, this will break, this will come, everything will happen. So the end. What is the moral of the story? The moral of the story is that the lone pair is not available on nitrogen, right? It is going to be involving in resonance, and that's the reason why it is going to be the least basic of them all. Okay, now this much extensive resonance will actually decrease the availability of lone pair to a very large extent, right? I would say that almost it is not even available. Okay, say, but I can have a lesser extent resonance like this in this kind of structure. Say I have something like this. If I have something like this, okay. Now again, what do you think will happen? From here it will start. Now this will break. So I would have had CH2 minus, uh, CH, NH2 plus. Please don't forget to put the positive charge on nitrogen. In this case also, the moment you do this, nitrogen should have a positive charge because it's losing electrons, right? So this would have been the resonance structure. Again, you see that the lone pair availability is not much, right? Now, if I ask you, out of these two, which is more basic? What will be your answer? Or say I'll mark it as 1 and 2. Which do you think will be more basic? Yes? Simple, right? What will be the answer? 1 or 2? Hello. Okay.
Two, sir.
Okay, 2. Fine. So one guy said, okay, I think, oh, how many of you are there? So many people are there. Good. Fine. So one guy said 2. Is there anybody who's going to support? Let me take a vote. Okay, let me check how many people are there first. There are 1, 2, 3, 4, 5, 6, 7. Okay, 7 people are there. There are a lot of chats. 1 second. It's going. 2. Okay, so 2 more said me 2. Okay, again 2. Anybody else? 1. So I got 1 vote for 1. Okay, so 5 of them. What about other 2? 2. One more. Good. Fine. So the majority of the votes we got for 2 is more basic, and the answer is right. This time we proved that we are better citizens, right? So yeah, so 2 is more stable. So not more stable, more basic, right? Again, it's all about the availability of the lone pair, right? Here you see so much resonance happening, right? So much resonance happening. Like the amount availability of lone pair is very less, right? But here it's just 2 resonance structures. Now, I would say this is the first resonance structure. This is the second resonance structure. Only 2 resonance structures are possible. But here you see, say this bond will come. So many will be there. 1, 2, almost like 4, 5 resonance structures will be getting for aniline, right? So definitely 2 is more basic than 1. Okay. Say I'll go for some more examples. Say I compare okay, so say this is 1, 2, and 3. Okay, take some time, right, and tell me the order of basic structure. Okay, this kind of compounds are what are called as heterocyclic compounds. Okay, so you have them in the syllabus, but not like the reactivity and stuff. Questions can come like this only. So heterocyclic compounds means in the ring, right? Other than carbon, if we have some other atom, those are what are called as heterocyclic compounds. I can even have oxygen coming, sulfur coming in the ring, right? So, anyways, just go for it and tell me what will be the order of basic strength for these three.
Sir, is it 2 greater than 1 greater than 3?
You're telling 2 is the most basic.
Yes, sir.
Okay, so 2 is the most basic. Okay, correct. And then 1, no?
Yes, sir. Then 1, then 3.
I think correct. Yes, it is correct. Absolutely right. Very good. Very good. Yes. Fine. We'll wait for. Okay, let me draw the structure properly. Maybe. All are 6-membered rings. So the answer someone gave, I mean, it's the correct answer, not secondary. Oh God. This. I'll give you 20 more seconds for you to arrive at your answers. At least check whether why this is correct in this 20 seconds. Availability of lone pair is more in 2. Yes, that's the answer. Okay, why is it available more, Kana? Why in 2 I have more availability of lone pair?
Sir, no resonating structures are possible.
Exactly, right? So people will get to the answer. Say in 2 there is no resonance, right? How say this bond will come here, make a bond, and then what? Nothing, right? So 2 does not have any resonance. So definitely the availability of lone pair on 2 is the maximum. So 2 is the most basic one. Okay. So now let me compare this and this. So obviously here resonance can happen. Say this will come here and this will break. I can write the resonance structure like this. Now I had a double bond here and there is a negative charge. Is it not? So there is resonance happening in case of 1. Okay, fine. Now let me go here. Now if I go here, you see there is more resonance. How more resonance? Now this will come. Now this will go here and this bond will break. So more extensive resonance. See, take some time to draw the resonance structures. Maybe I'll draw it for you. Wait. Okay, where did I have the bond? Here I had, here I had the bond. Okay. So say the first resonance structure would be this, right? So this will go and this will come a negative charge. Just putting like that. You can even directly put the bond if you want. So what I had here, I had a double bond, and here I had a bond, and here I had a negative charge. And obviously nitrogen should have a positive charge. People do not forget. I am forgetting. So and okay, sorry, not here. Here, nitrogen should have a positive charge. Right? What will be the next step? This will come here, and this will break. Right? So nitrogen is still having the positive charge with a double bond. Now the bond is formed here, and the negative charge is here. Okay. So what do you see here? In 3, this was 3, right? Now 3 had more resonance structures. That means the availability of lone pair is very much decreased, right? So obviously in 2 there is no resonance, in 1 there is less resonance, and in 3 they have maximum resonance. So the maximum basic would be 2, then 1, and the least basic of them all would be 3. Okay, so hope everybody got it. Why this is the answer? How do you approach these kind of questions? We will solve more questions. Don't worry. These are just trailers. We'll go for actual problem solving sessions at that time. You will see more difficult or not difficult, more interesting problems. Okay, so yeah, that's about the basic skills, people. Right? That there is nothing much to speak about anymore. If at all is there, we'll solve some problems. If we find new things at that time, I'll tell you if there is any. I don't think there'll be anything. Right? So this is the different. I mean, this is about the basic strength. Okay. So now we'll go for acidic strengths. We'll see what can we do about it. Right. Any questions of how this came? Okay. I hope not. Okay. So now, people, acidic strengths we will not be directly able to use for carboxylic acids. Okay. For carboxylic acids, resonance is it's already resonance stabilized, right? Say how is resonance stabilized? I have this carboxylate ion. Say this is my R or whatever it is. This is already resonance stabilized, right? So now what? This will come here. This will go. So again, there is already resonance that is happening, right? So what can I tell is whatever the alkyl group, if there is any possibility of resonance, that is not going to matter much. Okay, but where it will be matter, where it will matter would be in case of alcohols, right? So hope you should have studied that alcohols are also we even did, right? We even did the phenoxide ion, phenols and all that. So even alcohols are going to be say acidic in nature, little acidic in nature, but again less acidic than water, right? I think I gave you the order also, right? Alkynes, alcohols, water, then phenols, then your carboxylic acids, right? So anyways, so for carboxylic acids, nothing much can be done about resonance, but for your alcohols and phenols, yes, there is a huge effect of resonance in that. Okay, so let me take it into the picture. Say for example, if I had, like I'm just, if I have this alcohol, okay, so this is my enol. Does it ring any bell? Enol, guys? Does it
Tautomers.
make you remember? Ah, correct. Now tell me, is this the tautomeric structure of my keto form? Is this the structure? See, don't think like sir is juggling between the topics. It's because we have very less time. Obviously, it is tough for you to remember. That's why I'm making you remember. So just tell me, is this I mean this structure, can it be the enol form of my keto form? This is an enol, I understand, but is this a tautomeric form of the keto form? That's what I'm asking.
No, sir.
Good, right? If it was that, it would have been this. This one would have been the enol. Then only what you can say. Then you can put the double bond here. Then you can make the C double bond O. All that will happen. Now this is not the tautomeric form, so please don't forget. So you should have the CC double bond next to the oxygen atom. Only then I can say that this can involve in tautomeric. Okay, right? Cool. So anyways, right. So this is there. So now how do we go for acidic strength determination? We go for the stability of the conjugate base. There in basis it was availability of lone pair, right? So if I take the conjugate base, so this is my conjugate base after removing H plus. Now again, what you see is that I have 2 electrons. This will come. Absolutely wrong. Sorry. Right. So basically, this is not the okay, fine. Anyways, but if I have this, okay, O minus, right? This is going to be little more stable than say if I don't have the double bond, right? It is going to be little more stable than say this one. right? So than this alcohol, or say than this phenol, than this alkoxide ion. So this will be more, what to say, more acidic. Can you tell me why? Not because of resonance. Just now we saw resonance is not possible, right? So how do you prove it? How do you prove that this is more acidic, or say this this alkoxide ion is more stable than this one? How will you prove it?
Sir, inductive effect.
Okay, inductive effect. Correct.
CH2
How?
is a electron withdrawing group.
This one,
No, the one on the left, sir.
this
With
one.
the double bond.
Okay, this is an electron withdrawing group. Correct. How?
Sir, because C it will be CH if it's a separate um, radical, it will be CH2 2 minus. No, so that's why I'm asking.
Okay, all your answers are correct, but for the last part, yeah, this is an electron withdrawing group. So obviously this is more stable. All his answers are correct, but the last part, what you told, is not satisfactory. Anybody wants to give an answer, or you yourself want to give another answer? You're welcome. How will I go for it? You got the answer right. Obviously, this is more stable because the carbon atoms here are going to be electron withdrawing. Here they are electron donating. How will you account for it?
So is it in terms of hybridization?
Yes, correct. It is in terms of hybridization. Yeah, that's the answer I got from Sanjana. Sanjana says sp2 hybridized carbon is more electronegative. Absolutely right. Right? So you see that here I have an sp2 hybridized carbon atom, which is highly electronegative, not highly electronegative, compared to an sp3 hybridized carbon. sp2 hybridized carbon is more electronegative. That means it is going to pull the electron towards itself, right? So obviously the negative charge is decreased, and that's why this is more stable. Okay. See, I did a mistake, but in that you again got a question. Organic chemistry is such. Okay, it's very vast. But again, if you know certain things, like even the new things you learn can be easily understood. Okay. So, anyways, this is not what I intended to. I have to go for resonance. Fine. So, any questions here? Right. So obviously this is more stable because here I have an sp2 hybridized carbon, which is highly electronegative. Electron with the point. That's it. Right. Okay. So yeah, so the structure which I should have taken is this. This is obviously enol form, which can involve in tautomidism, isn't it? Right? Cool. So I have the O minus, right? So now this will involve in resonance. This will come. This will break, right? So how will be the structure? CH3, C. What happened? CH minus, single bond, CH, double bond, O. Right? So yeah, this is all. This is little stable. This is more acidic. Right? So the best example I can take is phenols, right? Obviously, right? Phenol and phenoxide ion, there is high amount of resonance happening. Say this will come, this will break, this will come, all these things will happen, right? So that's why we say that generally phenols are more acidic than the corresponding alcohols, right? Okay, now what we're going to do is basically we are going to concentrate on the benzene ring. Okay, we are going to concentrate on the benzene ring. If I put substituents here, right, if I put say NO2 or CH3 or something like that along with the phenoxide ion, right, how is it going to affect my stability? How is it going to affect my acidic strength? That's what we are going to see. Is that okay? Right? Fine. So, yeah. Or before doing that, let me put it like this. Let me ask you a question. Say, H. Okay. So say I have 1, 2, and 3. Quickly tell me which, arrange them in the order of acidic strength. Quickly.
So 1 greater than 2 greater than
Yeah.
3.
Yeah. Yes. 1 greater than 2 greater than 3. Absolutely. Again, the answer is more extensive the resonances, more the stability. So here you see there is more resonance. Right here I have only one resonance structure, and here I have nothing. So obviously 1 greater than 2 greater than 3.
Sir, what I did was I took the hydrogen outside and then did that, sir. That's how you do it, no, sir?
Obviously, the actual purpose would be to remove the hydrogens. Then you check for the stability. That's the exact way of doing it. What I did is correct.
sir.
What I did
Okay.
is little wrong. Yeah, this is how you should do it.
Okay.
Okay. Yeah. So yeah, we'll go for whatever I was talking about. Okay. So now please understand, people. Right. So in phenol or in phenoxide ion, for that matter, right? So the thing is, the motto of this is that you have to reduce the negative charge on the oxygen. That's the end point. That's the moral of the story, isn't it? Now that is already happening because I have resonance. Okay. Say now I have this. Say if I ask you that they compare this with this, right? This and this, if you want to compare, which is more acidic, which is less acidic. Okay, so it's pretty logical, right? How is it logical? Now, in the benzene ring, in the phenyl ring, if I have an electron withdrawing group, that will increase the acidic strength. Is it not? Obviously, electron withdrawing group will decrease the negative charge on oxygen. The same with if I have an electron donating group, acidity will decrease. And this is logical, right? Fine. So now please understand, if I have the group, either whether it's going to be electron withdrawing or I'm going to have electron donating, if it is going to be at the ortho position, right? If it is going to be at the ortho position, it is going to have both inductive effect as well as resonance effect. Is it not? Because it is very close to the charge, that feel O minus, right? So both inductive effect will happen, obviously resonance will happen, right? But if I'm going to have the group in the para position, say I have an NO2 here, right? Now in this case, yes, resonance is possible, obviously, but inductive effect, no. Why? Because we know the inductive effect is distance dependent. Is it not? Right? So obviously inductive effect you should not take care, but here obviously resonance is gonna answer my question of which is more acidic or which is less acidic. Okay, right. Now say if I have this in the meta position, actually what I'll do is, one second, I'll just rub it off everything and then we'll do it again. Right? So I have ortho, meta, and para. Okay, right? So if I look at the reference structures of phenol or phenoxide ion, let me do that first. Right? So if I look at the reference structures of phenol, this will come, this will break. So I have a negative charge. Where or not you see a negative charge? Negative charge is formed at, what is that? Ortho position. You'll see it in para position, again in ortho position. Okay, so you are seeing that the negative charge is getting formed at ortho and para positions, not in meta, obviously, right? So what you see, if I have an electron withdrawing group like NO2, if I have an electron withdrawing group like NO2 in the ortho position or in the para position, so what will happen now? Say if I write it like this, right? And I have a negative charge here. Okay, assuming there is a resonance happening, and the negative charge I'm putting it here. Now, what do you think will happen? Now, this will come here, and this will break. that is still more decreased. Is it not? The negative charge is still more involving in resonance if I have it. And same thing here. If I have the negative charge here, the same thing will happen. This will come and this will break, right? But in meta, if I have, it is going to do nothing actually, right? Because in meta, you see that there is no negative charge formed, right? So having NO2 at the meta position is just going to have only inductive effect, right? It's just going to have only inductive effect, right? Again, it is not going to be much of an inductive effect also because it is little far away, right? So if I ask you, right, out of these three, which is the more okay, arrange them in the order of acidic strength, and if I mark it as 1, 2, and 3, which will be your, I mean, what will be your answer?
1, 3, 2.
1 is the most acidic, yeah, correct. So 1, 3, and 2 would have been the answer, right? Now the reason is very simple. You want to give me the reason, Kana? Why is the answer?
So first one has resonating structures as well as inductive effect. So
Good.
it's more stable. So stability of conjugate case. And then
Yeah,
second one,
yes.
inductive effect is there and third one inductive effect is there as well as resonance is there, but inductive effect isn't that as strong as you
Inductive
see
effect is not there actually. Resonance is there, but inductive effect is not there because it is so many carbon atoms away. So no inductive effect. So resonance is there. Yeah, correct. Your answer is correct. Okay, go on. In two, what happens?
Second one only inductive effect is there, no resonating structures.
Yes, absolutely right. So hope everybody understood what he said, right? So here, since the NO2 group is a little close to my phenoxide ion, O minus, right? It can have both inductive effect as well as resonance is stabilizing the negative charge. But here, yes, it is stabilizing it through resonance, I understand. But since it is very far away from this, no inductive effect. I would say very, as I said, very negligible inductive effect, very, very small inductive effect, right? But here, the inductive effect is more because it is a little closer, but you see the negative charge is not formed at meta positions, right? So obviously NO2 has no role to play with respect to resonance, right? So obviously I told you resonance should be given the highest priority. And along with resonance, I have inductive effect also. So that is why you see this kind of order. Understood? Right? So yeah. Okay, now this is an electron withdrawing group. What if I have an electron donating group? Okay, we'll see that. What happens?
Sir, I have a doubt,
Yeah.
sir. Sir, does intermolecular hydrogen bonding have no role to play?
Intermolecular hydrogen bonding has any role to play with respect to acidic strength?
Yes, sir. Especially
Yes,
in the first
it
structure.
does. It does have a role to play because if I have 1 second, I can draw it for you. I would say more than intermolecular, intramolecular, I think will have more effect. But anyways, we'll see what happens. That's a nice question, actually. So if I have something like this, I have a lone pair, and say this. Okay, this hydrogen can involve in hydrogen bonding. Okay, actually, if you see what happens to this bond, see, I have an OH bond here, right? So, because of this temporary interaction, what do you think will happen to the OH bond?
Sir, it will
Will the strength of the bond increase or will the strength of the bond
decrease.
Decrease, right? So what can you say about it, about the acidic strength?
Oh, it will remain the same.
No, see, the thing I told you, right? When we compared HCl with with let's say OH, CH3COOH, right? We said that this is more acidic. Why?
Stability of.
No. That's what I said. First of all, you need to break the bond.
Oh yeah, yes sir.
Then you form the conjugate base. Then you check for stability. So first step is breaking the bond. So obviously here it is easier to break the bond. Why? Because the bond strength is less. Is it not?
Sorry.
The same analogy can be given here. Because of hydrogen bonding, this bond is getting weakened. Is it not? So obviously it is now easy to break the bond. So the acidic strength will actually increase if I have hydrogen.
Oh, okay,
Does
sir.
it answer your question?
Yes,
Right?
sir.
But again, this much detailed, they will not ask you. Do not worry. Right? But actually, very nice question. Very nice question. Right? Yeah. Cool. So that's thing. So now what we'll do is we'll try to go for an electron donating group, and we'll see what happens. Obviously, the opposite effect is what you're going to see. But anyways, we'll see it. O minus. Right? Say something like if I have an NH2 here, right? See, now look at this. If I have an NH2 here, it can show me inductive effect, right? So through inductive effect, it is actually getting stabilized. Is it not? Because the nitrogen is an electron withdrawing, NH2 is an electron withdrawing group. So definitely I can have the negative charge decrease due to inductive effect. Okay. So, but according to resonance, if I have resonance, right? So now what will happen? Now this can, okay, or this can come here, this can go here, right? All these things can happen. So through resonance, it is actually destabilized. Is it not? Through resonance, or I would say it is not. It is making sure that this is finding it difficult. The lone pair or the electrons here are finding it difficult to involve in resonance here. That is what is done by my NH2. Hope you're able to get the point. What I'm saying is, you can, okay, this is not the way to visualize, actually. Let me do it like this. I have an O minus. I have an NH2 here. Okay, say if I write the first resonance structure, now this will come, and say this will go here. Is it possible like that? Or okay, let me put it like this then. Okay, now what you see is that this is going to involve in resonance, right? And this is also going to involve in resonance. Okay, so what I'm saying is there's going to be a huge competition between your phenoxide and your NH2 to involve in resonance. The lone pair on them to be involving in resonance. There's a competition, right? So because of this competition, what is going to happen? This is going to push the electrons to this, and this is going to push the electrons to this, isn't it? Right? So thereby, the ability of the lone pair of the phenoxide ion to involve in resonance is decreasing. Okay, so that is why we see that here, if I compare it with your NO2, obviously if I had NO2 here, definitely this would have been very less acidic when compared to your ortho-nitrophenol. Okay, so generally I can say that electron donating groups are through resonance. Obviously, electron donating through resonance will obviously decrease the acidic strengths. Is it okay? So again, if I have your this thing in meta or para, okay, let me compare that also. Let me go for it. OH, say O minus or whatever it is in meta. Okay, 1, 2, and 3. Go for it. Tell me what will be the order of acidic strengths. Now it is little different than previous case.
Sir, is 2 most acidic?
Yeah, 2 is most acidic. Correct.
Sir, 2 greater than 3 greater than 1?
2 greater than 3 greater than 1. So again, 2 answers. Even Sanjana says the same thing. So 2 greater than 3 greater than 1 is what they're saying. So you're telling 3 is more acidic than 1. Okay, now I have to 2 and 3. Yes. 2, 1, and 3. Harish, do you care to explain why did he give this answer? I think you're typing, hopefully. Okay, Sri Harini says the same. Harish, resonance is happening here also, right?
Sir, is
I
it
think
due to
someone
the intramolecular hydrogen bonding?
no, Kana. Not because of that. See, I just told you. Yes, Sanjana said gives me the answer. It is because of plus I effect. Absolutely right. Right. See what happens here. Here I have inductive effect as well as resonance. Right. By resonance, it is decreasing. It is destabilizing. But through inductive effect, it is stabilizing. Right. Because it's an electron withdrawing group, so it is going to decrease the negative charge on oxygen by inductive effect. Is it not? Right? So obviously to inductive effect it stabilizes, to resonance it destabilizes. So obviously 1 will be little more acidic than 3. Because here resonance is there, which is only going to decrease. There is nothing to increase the negative, that is nothing to increase the stability. Right? But here inductive effect increases the stability. But here, and resonance obviously decreases stability. But here I have resonance decreasing the stability, but nothing to increase the stability of the phenoxide ion. Okay, so the correct answer would be this 2, 1, 3, and obviously 2. Why? Because it has no role to play. Right? NH2 has no role to play in the resonance. Right? So that's why 2 is more stable. Among 1 and 3, here I have inductive effect also, resonance also. Inductive effect stabilizes. So 1 is more stable, 1 is more acidic or stable than 3. Okay, hope everybody got the point. Why is it like this? Or you want to explain again? Why is it like this? Is everybody okay?
Okay, sir.
Yes, sir.
Fine, cool. Yeah, see, the same things can be done for basic strengths also, right? If I have aniline, right, and if I have an electron donating or electron withdrawing group, so again you can talk about basic strengths, basic strengths, determination, different orders of basic strength, the same thing. And now in that case, what happens? We'll see that. Actually, if I missed that point when we talked about basic strength. Right. So again, here in this case, electron donating group increases the basic strength, is it not? Because it's all about the availability of lone pair, right? So electron donating groups increases the basic strength, and electron withdrawing groups decreases the basic strength, right? Say for example, if I have NH2 with NO2 here, and say I have NH2 with uh, with CH3 here, right? So obviously, which do you think is more basic? Okay, 1 and 2. One is more basic. NO2 is what kind of group?
Electron withdrawing.
2 is greater than electron withdrawing group. NO2 is an electron withdrawing group. CH3 is an electron donating, right? So it's all about now the availability of lone pair. Last time it was decreasing the negative charge, right? Here it is more and more availability on the lone pair, more and more is the basic strength. So obviously this is going to be more basic than this one, because it's electron donating group increases the negative charge on your nitrogen. So this will be the order. Okay. So people, what is the time? It's almost 8:20, right? So we have completed the chapter actually, right? What we have to do is do a good number of problems. So next class will be entirely problem solving. Okay. I think or we can do 1 or 2 problems now, just for fine. I'll just take 2-3 more minutes, people. I'll not take much of your time, and then we can wind up. Okay, so I have 1, 2, 3, 4 carboxylic acids. Arrange them in the order of acid strength.
Sir, 4 greater than 3 great. No, yeah, 4 greater than 3 greater than 2 greater than 1.
Yeah, correct. Right. So the answer would be 4 greater than 3 greater than 2 greater than 1. Okay, correct, right? So obviously now it's all about the stability of the conjugate base. So if I remove the H plus from all of them, right? So wherever I'm going to have the least negative charge on the oxygen atom, there only I'm going to have maximum acidic strength. Now, what do you see? The carboxylate ion, the next carbon atom, if I write it properly, is having 2 chlorine atoms like this. So obviously, electron withdrawing group, decreasing the negative charge to a very large extent, right? But here, what do you see? There are 2 chlorine atoms, but where is it? Here it is in 1 carbon atom away. Here it is in the next carbon atom itself. Here it is 1 carbon atom away. Obviously, we know inductive effect is distance dependent. So obviously, that will be little lesser. So 4 after 3. 4 is 4, then 3. Okay, then here I have no electron withdrawing groups. Here I have only electron donating groups. And here, if you see, here I have only 1 methyl group, which is electron donating. Here how do I write the structure? Here it will be 1 more methyl group is also here, right? So 2 electron donating groups. Obviously, the negative charge is going to be higher in this case and lesser in this case. And this would have been the order of acid strength. Okay, hope everybody got this, right? It's very simple. We have done even tougher problems than this. This one is not even in the. Right? Okay, so this would have been the answer. I think, yeah, people, I think we'll stop with this for today. So next class will be exclusive for problem solving. So be ready with your notebooks. I think it will be on next Saturday, isn't it? So please go through all the things which we have seen, right? If you, hey, I don't know, are you guys taking notes?
Yes, sir.
Yes, sir.
Sir.
Okay. See, for I don't know about other parts of chemistry. Say a physical or inorganic notes doesn't matter much, but for organic notes is actually a must. Now, I hope you know why. So you can see how vast it is. So many small points there and there. I can say there can be exemptions and stuff, right? So it's always better to take notes. I know it's difficult. You are doing an online class. Taking notes is a little difficult, but at least now when I'm teaching, if you're not able to take notes, this video is recorded, right? So obviously you can go back, watch the video slowly and take notes. See, why am I telling you this is because reading through a book, right, and reading through your notes, there's a lot of difference in that. Reading through your notes will make it very faster. It's a very quicker process than to study a book or something else, or to watch the video also. Say 1 hour video, 1.5 hours of video. If you take the notes and if you study through it, it will take maximum of say even 20 minutes to even go through the entire lecture if you have taken notes. Okay, and it is obviously going to be helpful in so many different ways. Okay, so please do have the habit of taking notes, especially for organic. Now, the next 2 months, I would say next 1 month or 2 months, we will be doing organic only. Okay, so please make homework is not taking, please make sure you take it. Okay, so that's what I wanted to say. Okay, people, thank you so much. We'll see you again. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you.